What, yeah. Okay, generally one question. Okay, it started to record. Good. Uh, you guys have, is there a break this time for this, whatever, puja break or something? Is there something like that?
Yes, sir, 19th to 26th. But I haven't received any official intimation, so I can't be
Okay.
sure.
Yeah, 19 to 26, both days include 26, I think is Dasera or something. No, so that is probably.
Yes, sir.
So, see, basically, we have like this week three classes. So, I wanted to finish this anisotropic media. Okay. So, will you guys be okay if, say, on the 19th, we take a class? That I don't want to keep a topic like, three-fourths done and then carry on the next, 5-7 day break after that. Is it okay if I take I might take a class on Friday? That is whatever. Fridays gets, yeah, I mean, up to you. Friday class, or we can take it on Friday as well, whichever is
Sir,
okay.
I don't know about the class opinion, but I personally think that if we could complete
Mm.
it before the break, it
Yes,
would
that
be
would be better, right? It would be much better if you could basically have some closure, because what happens is if you miss like three classes and then whole thing gets out of perspective.
good.
Okay,
So I was saying that a class on Monday is not okay.
or is not okay. But
I
no, okay, so Friday is better, no?
right.
Friday is better. Let us see. So then, if people don't have objections, I think we can try to. I don't want to. I mean, see, I will take it as it goes. If I see that there is a lot of stuff left, then of course we can try to halt. But it's not too much actually. It's basically wave propagation and anisotropic media and some. Let us see. There is there is a bit of stuff. Yeah, maybe we can. So I'll try to sort of get some kind of a closure, okay? Because 3 days miss, 4 days miss actually, because 26th also we have a class, no? So 4 days miss. So you let me know whether Monday is better, or I think Friday is probably okay. But okay, so let me start sharing. Okay, so we will, as I think is clear to everybody. But now let me just still revisit my favorite picture, which you guys have seen unending number of times now, but I still want to go to it every time because somehow you cannot lose perspective. This is the thing, and that was like the model, which is encompassing the concepts that we are discussing in this course, that you're learning in this course. The aim being trapping a nanoparticle, a very very small particle that is immersed in some kind of fluid, and you have a very very tightly focused Gaussian laser beam which is emanating from here, which is basically being directed by all kinds of optics. It has these half-wave plates and polarizing beam splitter cubes, which are able to play with the polarization properties of this light. And these lenses are there, which help the size of the beam, control the size of the beam, and these are reflected. And then there is this dichroic. There are these two dichroic beam splitters, which have different properties in transmittance and reflectance depending on the wavelength. And then you finally have this microscope objective, which has a extremely small focal length, because it is like 100x. The magnification is very large, and magnification is like inversely proportional to focal length, so you know that the focal length is very very small. So another consequence of the focal length being small is that the spot size here is very small, so that you have a very very large optical intensity in this sample chamber, where you have these particles immersed either in air or in water or some kind of fluid, and you're able to trap or confine this particle using this light. And when you move this light beam, the particle also moves. So what we have covered till now is the reflection properties and transmission properties of these different objects, and we also have looked at how properties like absorption and transmission, which are related to the real and the imaginary components of the refractive index, So essentially, what we learned is when light is incident on a material, that material responds to light in a certain way, and it changes the behavior of light in the sense it changes the velocity by which in which light propagates through the medium, and that is responsible, I mean that is done by the real part of the refractive index, and there is the imaginary part which dictates how much of the light is absorbed in the medium and how much is let which is transmitted through. So that is very important because that is what dictates the thing that if I come with some wavelength of light which is incident on this material that I want to trap, and that if that wavelength corresponds to some kind of absorption maximum of this particle, then you can actually have this particle heated up because it absorbs a lot of light, and then it may get difficult to trap because it moves about very very fast. The Brownian motion is very fast, so you need a lot of a very very deep potential well in order to confine that particle. So that also is important. So what we will go from there is the properties of this half wave plate here, this polarizing beam splitter here, and these are responsible in changing, or the responses of these objects depend on the polarization of light that is incident. These are essentially examples of an isotropic media where the electric field, as we learned earlier, electric field depends, it behaves very very differently in different materials. In metals, as we saw, the magnetic field is much larger than what you have in vacuum or in dielectrics. Now in an isotropic media, uh, again there are very very different properties, and that is what we are going to study now. But before we study that, again this is the perspective that I was talking about. Essentially this is the part that we are going to study now, and what we shall just
Uh,
do before.
uh,
Yeah,
Sorry for stopping
yeah,
you.
yeah,
I
yeah.
have a unrelated question. Can you go
Yeah.
back to the diagram? I have been wondering this for a while.
Okay, yeah,
Uh,
sure. 1 minute. Yeah,
what is the role of M3 and M4? I can directly connect the beam to the
1 minute.
polarized beam splitter and then directly to D1.
M3 and M4.
I can just
Okay.
connect the
Yeah,
beam
so
to.
basically, so that is on a very, that's a typical experimentalist question, I might say. So Rohan, essentially when you try to see, you remember that again this, I hope people will enjoy this is a very technical discussion, very technical question that Rohan has asked, but I am very happy that he's asked this question. So remember, my target is to get this beam up to this. Okay, this is basically my target. And remember, if I am not able to absolutely get the center of my beam here aligned with the center of this objective, I'm going to do all kinds of very wrong things to the focal spot here. I will not be able to completely get the highest power throughput, because if I am slightly off axis, what happens is partially, the beam will can get cut. Because one very crucial thing we are going to learn, and which you guys who did the fiber optic experiment will know, is that the size of this focal spot here is any Gaussian beam. We're going to learn that, of course, but again I'll preempt that any Gaussian beam, the focal spot size essentially depends on the input diameter. Okay, so if I want to get the maximum amount of intensity here, I have to ensure that the input beam that is coming is the same size, or actually it's called overfilled. You have it slightly bigger than this objective, so that I get the maximum amount of the smallest focal spot possible here, and so that I get the highest intensity. Now if I want to ensure that I have the biggest, so yeah, the beam size is at least of this size of the input aperture of the objective, which means that if the beam is slightly misaligned with the objective, I'll have, the focus beam will actually get distorted, and if that beam gets distorted, I get all kinds of very very bad effects. Okay, so now if I want to sort of this, remember this, there are all kinds of things. The microscope, this is a microscope. Okay, so microscope is it's a large object. You've seen that, right? It's a pretty big thing, and this objective is inside the microscope, right? So I have to aim this beam out of the laser into that back aperture of the microscope. Thus, I need complete control over X, Y, and Z. In order to do that, you need at least two mirrors.
Sir,
And
are we
this is
talking
what,
about the near, far, far technique
yes,
that?
yes, something like that.
Okay.
Basically something like that, because near far far is of course a very particular concept when you have to, yeah, so essentially that is also linked to acha, this thing has got a bit distorted, I guess. I don't know, these edges are not matching, oh god. Yeah, so basically what we want to do when I taught you that near far far is essentially when we wanted to focus all the light from the laser into the optical fiber input aperture. Here essentially you have to get all that light again into a very sort of small focal length microscope objective, and you have to ensure that the XYZ, all three parameters of the input beam are completely under your control, and that for any optical alignment you cannot do without two mirrors. That is, just learn, I mean, just remember, just know this. Okay, you cannot do optical alignment, you cannot control a light beam in all three dimensions without using two mirrors. And that is very easy to logically defend, because remember, you are, if you have that control over, just, so it's like degrees of freedom, right? So you can at max control to control 2 degrees of freedom with one mirror, the third degree will get out. Okay, so that is the basic reason. We actually have, if you come to our lab, you'll see we have many more mirrors than two, because this distance is quite large, but at least two you need. That is a must. Okay.
Oh, okay, sir.
Yeah. I don't know how much others appreciated this, but this was a very good question. It's a technical question, but this is very useful. Okay. So before we go jump into directly into anisotropic media, we are going to basically finish off an important part in isotropic media. That is essentially the energy propagation. That is something which we have not. So I remember when we first, I think we introduced the concept of pointing vector. We looked at that. We generally looked at also things like how you have, the continuity equation, how it looked in the case of, in metals, when we studied how charges, the charges which are basically titillated, or any kind of, because metals are free charges, so we saw how the charge sort of decays inside, and then there are other collision, I mean, after each collision event we saw how the velocity becomes lesser, and then we did use the continuity equation in the optics of metals to some extent. But what is very important is, we did not really look at the continuity equation in terms of energy propagation, which is very useful, and which, where again the properties of the different kind of materials also comes in. Okay, so that is the last thing we do in isotropic optics, isotropic media, and that is essentially the energy propagation in isotropic media. So we shall firmly kind of wrap up our concepts on isotropic media when we end this today, and we start tomorrow's discussion basically from exactly here. So the question that I ask is there a continuity equation in energy propagation? Okay, this is the question that I ask. And so what do I mean when I say this? What does the can somebody summarize for me? Can somebody summarize for me what the continuity equation means? We know that it is like del dot j plus del rho del t equal to 0, right? This is what the thing means, and this is very crucial, because this is one equation which Maxwell realized, which sort of made him his biggest contribution that I feel is essentially the introduction of the displacement current for bound charges. So this was the basis of that. But what does it mean? Can you tell me? And when I especially, yeah, for any kind of continuity equation, what does it mean? What
It
does it mean?
that the charge is
If
not accumulated.
Huh? But in terms of this, you should say, yeah,
Oh, I was saying that charge does not get accumulated. Whatever leaves the surface is equal to the
yes,
rate at
yes,
which it moves.
exactly. That is well put. Yes, basically, I said somebody else was saying something. Do you agree with what Rohan has said?
yes, sir.
Yeah. So essentially, let me just summarize. So in terms of energy, what one can write is basically rate of change of energy enclosed in a volume that must be equal to flux of energy entering the surface which is enclosing the volume, right? Is this completely correct?
So minus the flux of energy exiting, right?
What is that? Huh? I mean, what is it? Yeah, but minus the no, but basically this is meaning that whatever change I have in the volume should be the same in principle of whatever is entering should be what is existing. I mean, what is exiting, something like that. But is this completely true
Yes, it's true.
for everything, all
No,
kinds of
no,
stuff?
sir. Like if the material is absorbing, then it won't be.
Absolutely,
Yes.
that is very true. And secondly, yeah, well, one can say that. But for what is another possibility? Absorbing
Uh,
is of course one, but can you think
I
of some other stuff? I
means
mean, some kind. So you're talking about losses, right, Anirudh? So what kind of losses can happen?
Sir, not only losses, there is also a assumption here that you should not generate new energy or new charges or something like that in the process.
That I am not. That is not. That is sure. I mean, I cannot generate charges by this. Absolutely. That and generating charges is rather non-trivial also, right? I mean, that is not quite easy. I mean, what we are saying is that ideally this should work, but there are some loss mechanisms. Anirudh has pointed out that absorption can be one, but what is another very, I mean, absorption, kind of putting it in this context, as you see, would be a bit different, but similar effects can be put in for some very kind of, not at the same mechanism as absorption, but some other loss mechanism which produces the similar kind of after effect.
So polarize, not polarization. This
No,
uh,
think of metals, na?
Heat dissipation.
So heat
Metals. Yeah, so heat because of what?
absorption.
Mm, no, we don't call that absorption typically,
Collisions
right?
in the electrons.
Well, typically we say that as this, right? Right? This is the typical term. The technical term typically is ohmic losses. So that is essentially what you're talking about. Is this not really absorption, but collision and yeah, so current, I that loss that comes because of Ohm's law, right? So this is the general sort of continuity equation which we have not really sort of derived, right? So that is what I want to let us see. I mean, this is very simple, but I think it is important that you still note how beautifully the mathematics works. But before that, we have to sort of there's some vector identities which are important, which I sort of have to just make you reminisce. And the basic identity is nothing but, just consider By the way, you can guess that I'm going to do this, right? So when I talk of energy, what am I going to talk about? So obviously this J will be replaced by what?
Pointing vector.
Pointing vector, obviously, right? So obviously I should consider A cross B mane it is going to be E cross H. But then I want you to sort of, what is this? ये क्या होता है?
It will be something of the form A dot del cross B plus
Not
something
plus, not
minus
plus.
minus.
Hey, these are very basic things that you should. वो शॉम में है ना? क्या क्या शॉम था? शॉम series, right? So then obviously I will take del dot E cross H is equal to H dot del cross E minus E dot del cross H. Now, obviously, let us write this. This is just rearranging the whole thing. E dot del cross H means H dot del cross E minus del dot E cross H. Right? Now, obviously, what do we have?
Sir, Rohan is asking what is H.
H. Hey, what is H? Arey, bhai, Rohan, what is H?
Is it magnetic field? I am just confirming.
Hey, no, come on. It is the E cross B by mu, na?
So
Magnetic field.
magnetic field intensity.
It is the magnetic field, correct. The pointing vector definition that we gave was del E cross B by mu. So B by mu man H. है ना? Right? So actual definition, if you go to field, then it's just E cross H. And it's easier to handle, I feel.
Why didn't you use directly pointing vector and then to take the dot product?
Yeah, because all those mu's and all, yeah. Why do you put constants? These are much easier to see, na?
Okay.
I mean, all those mu's and I invariably forget them also. And then you will start cribbing ki where did the mu go? You wrote a D, B and no mu. Anyway, so this is fine, right? Absolutely fine, na?
Yes, sir.
So very clearly, very simply what I'm saying is I'm having E dot J del cross H, E dot J plus E dot del D del T equals minus H dot. So here the fun actually comes after this in terms of the concepts, minus del dot E cross H. Okay, so that makes E dot del D del T plus H dot del B del T equals minus J dot E minus del dot E cross H. You already, I'm sure you're seeing that I already have my loss term here. And however, if I want to go to my final, my technical way in which we represent the continuity equation, essentially we need to take an integral, right? We need to integrate over volume V enclosing a surface S, right? Which basically means I'm going to write uh, oof, I hate it when it just takes off a little bit. E dot del D del T plus H dot del B del T dV is J dot E dV minus over V del dot E cross H dv. So again, I will use my, uh, let me go to a new page. So basically, that means if I now just put this, nicely together, this obviously means this E dot del D del T plus H dot del B del T dV is minus J dot E dV minus Gauss theorem use karo. This is going to get E cross H dot ds. Can we give the meaning of these? What does this mean? What do you think this means?
Rate of change of the stored energy in the electric and magnetic
Ah,
fields.
exactly. And we shall prove that also. That is exactly right. Rate of change of energy over volume V. This one is my good old ohmic loss. And this is, what is this? This is nothing but the flux of energy or power entering the surface, right? Now let us, this is very crucial, guys. This one is extremely important, uh, because that actually sort of tells you, the assumptions here are for isotropic, and anisotropic will not be the same. So what is crucially, so the energy is what? Typically, you know that your the WE, if I say, it is half epsilon E square, right? Or it's basically D dot E, right? Now it is only for isotropic media that we can write this. This is extremely crucial. This is very crucial. This you can write only and only for isotropic media. Okay, for anisotropic, it is not possible to write this because D and E are not in the same direction. That is very crucial. So it is not the same. This is not possible to be written for anisotropic media. So what we can write, however, if I write that as capital W, so if I write this as a small w, basically that this is the rate of change of energy that can be written as, actually just half we should put inside, half of, this is possible to be written, which means I can write this as that. Very crucial, right? And similarly we have WB, that is equal to del del T B dot H, right? Therefore from this equation, because we have this, we can essentially, using these we have something like del W del T plus del dot S equals J dot E, where W is WE plus WB, right?
Sir,
So,
means the rate of change of energy, there half would be there, right? E dot D when you changed, half will be there.
do you have a half?
Yeah,
Yes, sir. Half
half
will be there.
Oh, yeah, E dot D. No, if I take a 2,
No, sir.
ha ha
Half
ha
would
ha. Okay, so let me just complete that. Oh, horrible. Both of these. Ah, not here. So the same thing. Ah, this whole thing has been. See,
Sir, there is one way. Zoom your means
zoomed
whiteboard out,
outside every
and
time.
then
Ah,
okay,
but it's
and then
irritating, right? Every time you doing this is,
yeah,
when I have to get out, then it becomes small, is it?
yes, sir.
Wow, that is very. Anyway, so yeah, you're saying that get out, then this thing will become also small.
The size will remain
Anyways,
the
you
same.
can't. Yeah, but I have more control maybe. Anyway, so let me just. So this is fine. So basically, this becomes kind of half. So this is exactly what we set out to derive very clearly. Oh yes, sorry. And as you can see that uh, this J dot E basically will become for non-conducting media, for non-conducting media, clearly J dot E is 0, which means that you have del W del T. This is the well-known continuity equation, right? So this is, so that tells us that everything is fine. Our theory is sort of well rounded, but once we have written this, I will just sort of important. It's very important because when we do an isotropic medial start that some of these things will actually change, right? So if we can just sort of summarize what we understand as isotropic media. So can you think of them? What do you think you can write as summarize? What is your learning of what isotropic media has? I mean, or about what properties of the electromagnetic field are manifest? What should we write down as important properties of the electromagnetic waves or the fields in isotropic media? What should we write down if you are asked to sort of summarize? Because we shall see very soon that these are violated when you go to anisotropic media. So one of them I will write, then you shall understand what I'm saying, what level I'm wanting. So essentially E
D and E
D,
can be are linear.
ना linear मतलब क्या?
D is equal to sigma E. Then that's isotropic. Or
D sigma ही नहीं, epsilon ही.
sorry, epsilon.
So
Epsilon.
basically D, E and E, this is the basic stuff which I am writing, which are problematic, very problematic when we change stuff.
Sir, why is that? That J dot E represents loss, ohmic loss?
J dot E, no, but J, so
J
that is,
J we know is sigma E, right?
I'm just exactly, exactly.
From Ohm's law, J is sigma E, so that
Sigma
will
E, right? So
be zero
sigma E
minus
square,
sigma E square.
mm,
So that
which is essentially nothing but your V dot E type, I mean, I dot V dot E types, right? I dot V times, right? Is that
Okay,
clear?
sir.
Huh?
Okay.
So essentially, this is what level these might appear to you very trivial or obvious, but this is not. true if you actually change the medium. These are not true at all, right? So this is one. So what should I write after that? Very important learning.
So equations and all don't depend on the input polarization.
No, more basic, Anirudh. More basic level. I mean, what we kind of what made us be able to write this stuff.
D and D are in the same direction.
Exactly. E and D and B and H are mutually parallel. Very crucial. And the third one, which again you assume very nonchalantly, is that S is along K, right? Because we know that K cross E is B, right? This is very critical. Very critical. We assume that Poynting vector is in the direction of K. We shall learn in anisotropic media that it is very different. It is, the whole thing is very different. The moment you have E and B, which are sort of E and D rather, that are not parallel to each other, then things are very different. Very
Sir,
different.
this
So
is for plane wave, right?
yeah, we are dealing with what else? What other kinds of wave are you thinking?
So Gaussian beams in general, or any beam which have this Ex and Ey, the variation in Ex and Ey
Yeah, but
being
that
known.
yeah. So no. I this is not, see, even in Gaussian beams and all, in as isotropic media, you will not have differences. You will basically have similar things there. For isotropic media, you will have the energy along pointing vector. You can also assume like E and D are in the same direction. See, plane wave, finally, see, when you go to Gaussian and all, you are essentially just limiting the plane wave and getting some different types of modes and all. Okay, so unless you change the isotropy of the medium, some interest, mostly this property will not never emerge from
Uh,
anything.
okay.
Okay, this is very important for whatever electromagnetic field that you take. E and D are going to be parallel. Of course, the forms may be different. I mean, the form that you have for E for a plane wave and the form that you have for E for a Laguerre Gaussian or a Hermite Gaussian or basic just fundamental Gaussian mode, those will be different. But the displacement field that you create by the electric field, that will still be in the direction of E. Okay, so that is an important, I think, concept for everybody to appreciate. Okay.
Sir, but number one might not hold for bounded beams, right? Uh,
Yeah, man, you're saying that there is an EZ component also, right?
yeah,
So
yeah, yes, sir.
yeah, that I will agree is a bit iffy because you have a parallel component. See, this way, okay, let me write what you're saying. This is very crucial. See, I mean, you guys are, I mean, I can assure you, Chitradeep, was it Chitradeep or who was it?
Sir, Anubhav.
Anubhav, yeah, you have
That was
same
Anubhav.
voice as Chitradeep, very similar voice. Anyway, so this, see, I mean, 95% of students at your level would not have raised this question. That is good. I feel at least vindicated because everywhere that typically optics is known or where people use optics, this is like a very big thing. This Paraxel approximation, people do not realize how important it is, but everybody tacitly thinks of this. Okay, it's good that you guys realize that that is not true. When you have any kind of bound, these are very interesting, and I really I hope somebody will cover this in the talks. But reality that we sort of study. So there is this very big, very sort of good researcher, solid researcher in this field of exotic optics of angular momentum of light and all this called. So this guy's name is Konstantin Bliok. Okay, So he has this major kind of, so so when I was at one of these SPIE conferences at San Diego, it was way back in 2015 or something. So Bliok had an invited talk, plenary talk sort of. Okay, so and his main thing was that he kind of believes that this pointing vector treatment is rubbish. It should be discarded. It should not be taught even in schools. Okay, so he was so aggressive. Okay, so he said that, so he has this thing of angle of momentum. He talks about momentum, canonical momentum. Okay, that is a part which is basically a momentum which is similar to the quantum mechanical momentum, that is that IH cross del, which he talks about is kind of akin to the orbital angular momentum. And the second one is the spin angular momentum. So he can show that in case of a plane wave, you will get everything that you talk about in the pointing vector algebra. Whatever you get, you can get everything using those concepts. But it is not bound by all these stuff. This 1 and 3, it does not assume. It absolutely does not assume. Okay. So he was like, his whole like 1 hour lecture or whatever 45-minute lecture which went on for 1 hour was essentially based on that how angular momentum, I mean this concept of canonical momentum and spin momentum, why those should be the basics, which should be the the language of optics, of wave optics, and not pointing vector. And after the end of his talk, there was this other researcher who is he's like he's, I think he's now England in, so Bliok at the moment I think is in Australian National University or something. Because he keeps on changing. Okay, he was never fixed at one place. He was just going all almost like a globetrotter. At the moment, I think he has fixed at Australia somewhere, ANU or something. So there is this other guy called Masood Mansooripur. So he's also a very, he's immersed in this wave optics research, very very high end. So they are not this kind of simple stuff anyway. So that guy is a senior guy. He's actually elder to Bliok. He's older than all of us. He just stood up and say, "You are speaking nonsense." He just said that in a conference. Okay, this is rubbish. I mean, what you're saying, of course, that is true, but that does not mean that the pointing vector should be discarded. Because think of how powerful it is. All your thing of having the Z component and all that. I mean, come on, you talk about Gaussian beam. That Z component is ridiculously small, right? That is almost vanishing. You can everything 95% of optics as we know it absolutely can be solved using the pointing vector. What you are saying is just the this is just the snobbishness of a theoretician. And there was complete silence, and there's a whole hall filled with people, total silence. And then Bliok says, okay, you are perfectly entitled to your opinion, but I think what you're saying is crap. And then of course both of them agreed to that. They agreed to differ, saying that but of course Bliok was not wrong, and in some way Mansooripur was also not wrong, because it is a fact that as long as you are in this approximation, this is a mighty powerful approximation, I can tell you. I mean, even our LIGO, that is measuring things at like 10 to a minus 30 kind of effects, right? Even that works in this. Okay, so discarding the pointing vector that way, is very strong a statement, which is probably not absolutely warranted. But what Bliok said was correct. In the pointing vector treatment that way, and considering everything in that frame of mind, is not completely correct. That one can say. But again, you can argue that physics finally works completely in approximations. That is how we can tune mathematics to sort of obey physical phenomena, to sort of explain, rather, to explain physical phenomena. But again, you cannot compromise, or you cannot discard correctness as well. So it was a very interesting argument that I remember. So you guys are interested, so I can tell you that so Konstantin Bliok has a extremely interesting paper in Nature Communications, where he nicely discusses all this. I think it was, I will update. It was basically on extraordinary angular angular momentum of light. So just search this. It is, I believe it is 2015 or 6. I don't remember that. But people who are interesting, just put extraordinary angular momentum of light, Konstantin Bliok. You will get that paper. You need not study the whole paper. The first 3 pages are fantastic, fantastic, because they really take you through this whole journey, okay, of what Poynting vector means, and yeah, but rather, sorry, what the this angular momentum of light, what it means, and how you can represent this in a sort of a you know an absolutely watertight manner, where all these issues of z component and all are taken care of. Beautiful. And also, yeah, very nice. I don't want to get into that discussion, but anybody interested, please look at this paper. And he has more papers after this. Okay, so this kind of ends our treatment with with isotropic media. So we will start an isotropic media today. I don't want to get into too much, but just the absolute basics again I will write down, and we shall start this in earnest in the next class. By the way, yeah, this was just an anecdote, so I don't know, but if anybody has questions, yeah, it's probably better we discuss offline, because that's not going to be useful for the class. But any comments anybody has? I don't think you guys are aware of this canonical momentum and spin momentum and all, but it's very, very interesting as a subject. And these are the new things in very, very sort of fashionable. I mean, absolutely sort of current things in optics at the moment. Okay. So
So is this in quantum optics or wave
no,
optics?
completely wave optics, not quantum.
Oh,
So Bliok actually
no, you were
uses
talking
quantum
about
phenomena.
the,
Yeah,
yeah.
so he makes a beautiful connection actually. Makes wonderful
Oh,
connections. Okay, how you can try to. You should just look at this, man. I mean, there. Maybe I will upload this in your thing. Maybe I will upload this. I don't think you'll understand much of it. Don't try to go into too much of depths, but at least the first 3 4 pages and the references from there, they are wonderful. So at the end of the class, I'll upload that paper. I think it's important. Acha, so can somebody tell me how one can represent isotropy by an equation? Isotropy and homogeneity by 2 equations. Fatafat. I have a vector A, which is a function of some R. So what is isotropy? What is homogeneity?
Sir, isotropy should mean that if you transform, like whatever equations govern the vector A, uh, if you apply a transformation of rotation in certain direction,
Is this
then
fine?
yeah. So the transformation shouldn't change the form of the equation.
Absolutely. Which is basically there is no dependence on direction, right? In a very, very basic sense, if I say that the properties are independent of vector R, kind of, right?
basically
And
scalar
if
function.
yes, correct. And if it is man, this rubber is really horrible, no? What will that be? Isotropic and
Constant.
That will be
exactly
not even dependent on
constant.
R.
It is basically a constant. So very crucially,
Sir,
which
but
is a
what is
sub
A here exactly?
k constant. I mean it's
No, no,
constant.
like A,
Ah,
whatever, what is A in this whole thing?
it is some vector, some
No,
something, some, it can be field, it can be polarization, it can be some kind of a
it has to be something that is a property of
property
the
of the
material.
medium. Yes, correct.
Yeah,
Property of that. Yeah, yeah, that is a good point. Yeah, okay. Some
it can't be like electric field. Electric field need not be uh, like electric field need not be phi independent just because the material is.
right. That is right. That is right. So it is some kind of a. Uh, yeah, yeah, that is correct actually. So yeah, you're right. I think it is important. It is essentially a property of the medium. I think that is what we should try to say. Or can we say that? Uh, well, No,
So
but see, no, but
was,
no, no, no,
what I was saying was that
but Anirudh, even for electric field, if you're going around phi, then along phi it is not going to change, right?
sir, we can have a Laguerre Gaussian mode that is going through an isotropic medium, right?
Huh?
So that will have the electric field will have phi dependence in that, right?
Yeah, yeah, electric field, no, but the surface, the in the medium, the electric field will not get sort of different properties of the medium, will not sample
Ah, exactly.
different
So
properties of the medium in different directions. Yeah, so what should we name this? Yeah, that I understand what you're saying. It is not that the electric field itself does not have different properties, but the
yeah,
electric field does not experience different properties.
I need to say
Sir,
that
there is a easier way.
Huh.
Any vector of if the value of the vector at r equal to 0 or r equal to some any point xyz, both are equal, then it is called isotropic.
no, that's not it,
No, no,
right?
that also is
Um,
not correct.
That's
Yeah,
what
because
exactly what I
that
pointed out.
exactly
So
is what he said. Yeah, right, right. There is a phi dependence on
like
the
a
electric
Gaussian
field.
beam going through an
Uh,
isotropic material won't have the same electric field value at
correct,
different
correct, correct,
positions
correct, correct.
because
That's totally
the
right.
material is not
It is,
isotropic.
yeah. So it is basically that the material properties in different directions are not different. That is the whole thing
Yeah,
of
sir.
this thing.
But my initial statement was that whatever equations are there governing the like let's say we're considering electromagnetism. So whatever
Uh,
equations govern the electric and magnetic field, those
uh,
equations should be invariant under
uh,
rotation or
right,
whatever.
right, right. That is fine, but in the sense that can we put this as a material, see, because I find this easy to visualize because it basically tells you that the properties of the medium are independent of the direction,
Yeah,
whereas this one tells you that the
then
properties
you
are
need
the
to
same.
specify that A is a property of the medium. Then
Yeah, yeah, but something like maybe, yeah, I think it's important to write that I agree. So I think it's not correct to say that A is a vector, right? Maybe I should not write that A is a vector. Ah, damn. Okay.
So doesn't it
uh,
mean when you just write that A of R vector is A of R, you're just showing that it is rotationally invariant?
yeah,
Because
yeah,
I
yeah,
think this
absolutely.
only
Yeah, yeah,
signifies
yeah,
it's
yeah, yeah,
rotationally
yeah, yeah,
invariant.
yeah, 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 exactly. Exactly what Anirudh said is exactly the same thing. Under any
So
rotational transformation, there is no change of the equation. I go to a new frame of reference where the equation is exactly the same. Where again, however, yeah. So essentially, if I say this in this way, yeah. So we're trying to finish something.
uh, sorry.
Yeah, but you, Priyanuj was saying so something. What?
Yeah. So I was trying to say it is enough for the equations to be rotationally invariant
Ha,
to
ha,
be
ha,
called
ha, ha.
isotropic.
Yes, yes,
So
correct,
nothing else is required.
correct, correct. But
Because
see again,
transformation can mean others, other
yeah.
transformations
Ha,
also.
ha, oh, oh, okay, okay.
No,
Oh,
sir,
One thing is there, sir, that when something called isotropic or anisotropic media, there
ha,
has to be some reference. Means isotropic
ha, ha, ha.
to the light. Means that's why to the light means then the that epsilon variation coming out.
Ha,
So
ha, 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 ha.
always A is to be the property,
It's a
not the
property.
media.
Exactly, it's
Yes.
a property of the medium. That's why I think it's important. By the way,
Yes.
so one thing also should be clear to you: key one implies the other, and but the other does not imply one. So which will be which? Which will imply which? I mean, one will imply one has to imply the other, but the other does not imply this. You understand? If I say isotropy
So
homogeneity,
homogeneity.
hey, Bishojit, you don't say. Bishojit
homogeneity
cannot say.
implies
I
isotropy.
Right. So homogeneity implies isotropy. Very crucial. Not vice versa. You can have a isotropic but inhomogeneous medium. That is very, very possible. Isotropic homogeneous is the simplest case. Okay, we have struck 7. So I had promised that I would not go beyond exert you too much. Yeah, in fact, yeah, I don't think we'll go too much. I think 10-15 minutes extra we'll go. ठीक है. So I think we shall start this thing completely fresh tomorrow. And yeah, okay, great. So I'll start from this slide itself tomorrow. So I'll not upload this slide maybe. Yeah.
Sir,
So any
sir,
questions? Ha,
yeah,
bolo.
this means as per the vector you are saying.
Hmm.
So entropy, what it means. So if you have a means at some r x y g, okay, you have a value of that vector. So
That
if
is fine. If you say that this vector is that property of the medium, that property of the medium, what you said would probably be right. That property of the medium does not depend on the direction at which you are sort of
you're
taking or
measuring
measuring or
entropy,
something. Yeah,
yeah,
yeah, that is fine. If I say that A is the property of the medium stuff, it
yeah,
cannot be electric field or something. The electric field may absolutely have a phi. In fact, that is the thing, right? In an anisotropic medium, if you come with an electric field that does not prior to entering the medium have any directional dependence or have any phi dependence, an anisotropic media can actually cause phi dependence to come in,
yeah,
right?
yes,
And that will basically generate orbital angular momentum in an electric beam where there was nothing of that sort previously.
yeah,
Okay, so that is
yeah.
very important to understand. Huh.
And what Anirudh was saying is was like means I think rotational invariance of this
That is the
Hamilton.
same.
Yeah, so it's just approaching the same problem with a
Yes,
different
yes,
perspective.
yes, yes, absolutely. So any equation which is rotationally invariant, that has to sort of obey this kind of thing. So any frame of reference that you go, if you rotate the frame, you get the same set of equations that you had in the previous frame.
Yeah.
Okay, ठीक है. अच्छा, I have updated your that वो क्या है वो that submission date of the assignment to cutoff date. I've made 18th 12 p.m. ठीक है. That is what somebody wanted. Okay, ठीक है. चलो then. Any other stop presenting? Stop presenting कुछ नहीं हुआ. Okay, so any other questions or else we meet tomorrow?
So I had an unrelated question. Like you can stop
हाँ,
recording.
stop
Like
recording. Okay, हाँ.